Okay. What are we gonna do today? Okay. Today's objective is just to write mole ratios so you can use them as conversion factors when you're solving stoichiometry problems. And I'm gonna start over here with a word equation. Iron is reacting with oxygen to produce iron trioxide. Okay, that's the word equation. If you want to translate that into the chemical equation or skeleton equation, this is the skeleton equation. Now, what happened with the skeleton equation? That is, you look at the subscripts over here is not balanced. How you gonna balance that? Using coefficients. You already know that. This is not new. This is all stuff that you learned while you were in school. I was explaining all of this. And I remember that when we were addressing the topic, balancing chemical equation, I was like reading the balanced chemical equation, and I told you that in the future you'll have to use that. That's what we're going to use today. We're going to start using the ratio, using the coefficients that are balancing the equation as conversion factor. Okay, so how are you going to read this balanced chemical equation? Okay, so when you have a balanced chemical equations, the coefficient, they're telling you the number of moles of the substance that are involved in the reaction. What I'm talking about substance, because remember that you can have elements to form compounds, like in these examples, or you can have compounds to form new compounds. So in general, there are substances that they're going to be reacting to produce or to form new substance. So how are you going to read this? One more time. So if you have, see, 4 moles of iron reacting with 3 moles of oxygen, then 2 moles of iron trioxide will form. Mis Ramos, what I'm doing with that information? Okay, that's today's class. Okay, Mis Ramos, what are mole ratio? Because you keep talking about mole ratios. What are mole ratio? What is a mole ratio? It's a ratio, you have that over here. It's a ratio between the number of moles of any two substances in a balanced chemical equation. Mis Ramos, can we have mole ratios if we have an unbalanced chemical reaction? You think about that. In an unbalanced or in a skeleton chemical equation, do you have coefficients in there? So it's impossible for you to have mole ratio or to write mole ratio when you have a skeleton equation. You need the balanced chemical equation in order to find the mole ratios. Why mole ratios are important? And I'm going to read this balanced chemical equation one more time. For 4 moles of iron that are reacting with 3 of oxygen, how many moles of iron 3 oxide produce? Only 2. Okay, but let's say that instead of having 4 moles of iron, I have only 2 moles of iron. Am I going to be able to produce 2 of iron trioxide? No. So if I have 2 of this, I'm going to be able to produce, with that amount of iron, I'm going to be able to produce only 1 of this. Yeah, I don't see if you see the connection. If I'm decreasing this by half, what's going to happen to the products or the amount of the products? They're going to decrease by half too. Let's say that instead of having 2 of this, okay, I have 1/2 of this. See that? If with 3 I made 2, with half of 3, how many mole of iron trioxide I'm going to be able to produce? And that comes from the analysis of the mole ratio. Now, let's say that you don't have half of 4, that you have 5 mole of iron. How many moles of iron trioxide are you going to be able to produce? Do you know that? Okay, and that's why you have to start writing mole ratio, because mole ratios, they're gonna be used as conversion factors. Yeah, I'm gonna show you an example. I was explaining that to you. For 4 moles of iron, how many mole of iron trioxide can be produced? 4 mole of iron, no, 2 mole of iron trioxide are produced. This is an example of a mole ratio. Why? Because it is the ratio between the number of mole of any two, in this case, one of the reactants and the product, any of the two substances in a balanced chemical equation. So for 4 moles of iron, I'm going to be able to produce 2 moles of iron trioxide. But let's say that I don't have 4 moles of this. Okay? I have 5. How I'm going to use this mole ratio to find the amount of the product that's going to be produced? Remember that always you're going to start with what you have. Moles of iron. Always you're going to multiply by a conversion factor. You want to get rid of the mole of iron. So the mole of irons, they go into the denominator. Moles of iron. 2 moles of iron trioxide. So if you want to know the amount of iron trioxide or the amount of mole of iron trioxide that are going to be formed when you have 5 mole of iron, you're going to use that mole ratio between iron and iron trioxide just to find that amount. How you going to find that? You know that. You can put this over 1 and then you solve it. And here I think that you have 10 over 4. I think that that's 2.4. 2.5 moles of iron trioxide. See that? This is what in chemistry we call a stoichiometry problem. You were able to use a mole ratio to find the amount of the products that are going to be produced given certain amount of one of the reactants. See how I was using here the mole ratio? Okay. Now, okay. So writing mole ratios. Remember, the first, you need your balanced chemical equation. Once that you have your balanced chemical equations, you can start writing ratios by using the coefficient of the substance in that chemical equation. Yeah, I'm going to start over here. See? For every 4 mole of iron, how many moles of iron trioxide can be produced? 2. Okay? And that's my first conversion factor. But the opposite is true too. So for 2 mole of iron trioxide, 4 mole of irons are needed. Why this one and the reciprocal? Because sometimes, given the amount of the products, you have to find the amount of the reactants. That's why you can use the reciprocal of the mole ratio. Now, for 3 mole of oxygen, which is the next reactant, how many moles of the product? 2. And the reciprocal. But you have also a relationship between the reactant. You have a ratio. For 4 moles of iron, how many of oxygen do you need? 3. Let's say that you have, this is for the future, let's say that you have 4 mole of iron, but then you have only 1/2 of oxygen. Do you have enough oxygen to react with the iron to form 2 mole of iron trioxide? And that's the idea. See, because after learning how to solve a stoichiometry problem, you will have to find the limiting reactants. Okay, so how by looking at your equation, how you're gonna be able to find the amount of mole ratios that you have in there? Easy. See, count over here. You have 1, 2, 3 plus the reciprocal. So in an equation, when you have 1, 2, and 3 substance involved, you multiply that by 2, then you're going to find the number or mole ratio that you can write from that chemical equation. Now you have 4 substances that are involved, 1, 2, 3, 4, multiplied by 2, then you will have 8 mole ratio. The same thing will happen since you have 5 or you have more than 3 substances that are involved in a chemical reaction. You multiply the amount of substance by 2, and then you will get the number of, or you will get the amount of mole ratio that you can write from that chemical reaction. And this is one example that one example of what you can find in your classwork. Okay, so you need to find a possible mole ratio for the following chemical equations. The first step is just to analyze what you have in there. You have to ask yourself, if my chemical equation balance, I don't think that that's balanced, because over here you have 1 chlorine and over there you have 2 of them. And you have 1 hydrogen over here, and over there you have a 2. But this is, let me see, this equation is too easy, see, because with a 2 in front of the acid, you will balance your equation. You have 1 syn, 1 oxygen, 2 hydrogen, 2 hydrogen, 2 okay, so it's already balanced. Once that you have your equation balanced, you need to count the number of substances that are involved. 1, 2, 3, 4. So 4 multiplied by 2, 8 mole ratios. Okay, so I'm going to start with the first one. 1 mole zinc oxide of zinc oxide will yield 1 mole of zinc chloride, and the reciprocal, 1 mole of zinc chloride will be produced after 1 mole of zinc oxide was used. I'm going to continue, see? I'm going to apply the distributive property because I don't want to get confused. First reactant with the first product. Reactant with the second product. So 1 mole of zinc oxide will yield 1 mole of water. And the reciprocal, 1 mole of water will be obtained if 1 mole of zinc oxide was reacted. Continue with the second reactant. If 2 mole of hydrochloric acid were used, only 1 mole of zinc chloride will be produced, and the reciprocal, 1 mole zinc chloride will be produced if 2 mole of hydrochloric acid are used. Okay, second product, 2 mole of hydrochloric acid will produce 1 mole of water, and the reciprocal, 1 mole of water will give you what? 1 mole of water will give you, will be produced if 2 moles of hydrochloric acid were produced. 1, 2, 3, 4, 5, 6, 7, 8, and you may think that you're done, but you're missing something in here. So in this case, that 4 multiplied by 2 doesn't apply, because you don't have a mole ratio that is relating the products by itself or the reactant. So I'm going to use that right now. So 1 mole of zinc oxide, we have to react with 2 moles of hydrochloric acid, and 2 moles of hydrochloric acid will have to react with 1 mole of zinc oxide. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I'm going to relate the products. 1 mole of zinc chloride will be produced together with 1 mole of water. The same time, the reciprocal. 1 mole of water with 1 mole of zinc chloride. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, and now I see the pattern here because I was using the wrong parent. Yes, pattern. Okay, so you have 4 substances that are involved. You take away 1. 4 minus 1 is 3, so you multiply 4 times 3, and then you're going to have 12 moles ratios, which apply when you have 3 substances involved. You have 3 substances involved. You take away 1. 3 minus 1 is 2. When you multiply by 2, then you have 6 mole ratio. And that's the pattern, or the pattern that the pattern that you see when you're looking for mole ratios.